Good morning, everyone. Just want to go through a little bit of who we are in case you're unfamiliar with Thornton Tomasetti. We're about a 550-person structural engineering company that does work throughout the United States and also overseas. The biggest part, and obviously you can read our values and our visions and that, but the vision is what I think is what I like to dwell on. Is we always reinvent how buildings are imagined and built, and in this case, when we're dealing with Tekla structures, how we deliver them as well. We have 12 U.S. offices and several overseas offices. The areas we practice in structural engineering are building structure, which involves anything that's a new structure or a new building. Building skin, which deals with the exterior of the building, curtain walls, glass walls, building facades, and also building performance, which is anything that happens to a building or anything that needs reconstruction of a building after it's already been built. Those three things roll into our market sectors, which, as you can see, are probably almost everything that deals with needing a structural engineer. A little bit about the BIM concept. BIM's been a key word out there for many, many years, and if you ask anybody, they all have a different definition of what it means to them. Traditionally, it's kind of a linear process. It kind of starts or originates with the architect saying, hey, I want a 3D model. He then says to the structural, we need you to make a 3D model with us so that we can coordinate our drawings. So generally, who's been involved in the past has been really the architect, the engineer, and the mechanical. And what's usually involved is we've got a little clash detection, some three-dimensional modeling, and then maybe coordination of mechanical systems, but typically it was never really handed down very well to the contractors or to the final end user to produce the building. So it was a very linear process. I like to look at it a little differently now in that, although this is a stacking thing, as an engineer, I'm thinking, how can I improve the project? How can I help add value to the project? And so all those items I've got under the engineer as far as connection design and skin consultant and erection engineering, steel detailing, concrete detailing. If I can provide some of this information downstream to the fabricator or work with the fabricators and the contractors to develop this into our models from the beginning, we'll be able to deliver a much more usable product. So what we'd like to do in the end is get a single BIM model that everybody is involved in, everybody has a part of, and everybody understands, and it works well from the start of concept all the way through design. So what I've been pushing a lot is the time to embrace the model sharing. Now is the time to embrace the model sharing and designer-contractor collaboration. That's after all those items that I feel engineers can help provide in delivery of project systems. We've developed in-house for Thornton Tomasetti what we call a construction support services division, which also deals with advanced project delivery. Some of the things we do in that are during design is we provide detailing of the Tekla model. We can do just several different phases. We can just do a mill order model where we're connecting up all the pieces where eventually we turn the model over to the fabricator or the contractor. We can do phase 2, which is designing the connections as well as connecting it all up and then turning it over to them, or taking as far as phase 3, which is actually producing the actual shop drawings with the fabricator input. We also deal with precast and cast-in-place concrete detailing or modeling. So what we can do is, if we're using Tekla structures during an integrated modeling service, we use steel detailing during design using Tekla structures. So we produce a single model that models all the steel. We then produce the design documents directly from the model so that we don't have two separate formats or anything. So we don't have a Revit format or an AutoCAD format and a Tekla format. What you see on the drawings is actually what's in the model. What you get in the model is actually what's on the drawings. And as I said, there's several different levels that you can take it to depending on how the project is structured or what seems to make the most sense or add the most value to a project. We break up our modeling kind of in a phase 1, which we define as sort of a mill order model. It models all the individual pieces point to point. You can create your advanced bill of material. Actually, if you turn it over prior to bidding, it gives you a very good, accurate material bid takeoff. and reduces the overall schedule, just because now you don't have somebody sitting there doing takeoffs on all the models. You can just run a report, you can get what's in there, you can see what the complexity is as you're trying to connect everything. This is just another shot of the design drawings that can be produced directly from the Tekla model. You know, some of these buildings that we work on are rather complex geometrically, so sometimes we do isometrics, put isometrics right in the drawings, which help define a little bit more how it needs to be erected and constructed. Phase 2 is kind of an advance to phase 1. It's basically a connected model. So now we've designed the connections, we've actually connected it up in the model. So now you can understand what the complexity is involved with connecting the model. We also use this a lot when we coordinate with the architects. The architect will have a glass wall and maybe have some vertical bracing behind it, and they want to see, they don't want to see just the sticks. They want to see exactly, you know, what's that gusset plate look like, because I think they've all probably had a time or two where they thought they were just getting the members, and all of a sudden they go out there and they've got this great big connection plate right behind their glass wall. So we use this model a lot in coordinating with them to conceptualize what the connection will look like, what the details will look like, how much of the gusset plate, do we need to sculpt the gusset plate. So we use that for coordination with the architect too. Phase 2 design drawings, basically just taking those connected models and helping to define the complexity to the contract a little bit easier. You know, if we've connected the model, they can see isometrically, you know, which piece goes in how it goes in, how it needs to be fabricated and erected, and they can get a better quantity takeoff again from the number of bolts and gusset plate thicknesses. They're not guessing as much as to what the connection will be. And then of course there's drawing, phase 3, which is actually the actual shop drawing extraction, which is what most people are used to saying it as. Basically, a lot of times we'll delegate this to the, a lot of times it's delegated to the fabricator. We'll connect the model, we'll model the members, we'll connect it all up, we'll hand the model over to the fabricator, and he'll take it from there using maybe his preferred detailer or being able to incorporate some of his specific fabrication preferences that maybe we hadn't put in the beginning. We have on several jobs self-performed the actual shop drawings. Usually they're more complex jobs where there's a schedule impact. We're working with the designers hand in hand a lot more, along with working with the fabricator as we go through. And this is just a picture of that's the Queen City Tier. It's probably about 100 foot tall. Pipe arch trusses, about 100 foot wide. It sits on top of a 42-story building in Cincinnati, Ohio. And so just all the fabrication cuts and all the bird mounts that you have to do on all this pipe stuff was rather involved, rather detailed. So it was rather complex for detailing the steel. We detailed all that in-house with the fabricator, providing input and helped do layout templates and everything else in the shop. Precast and concrete modeling, becoming more of a need or a want out there. Steel modeling has been going on for quite a while, but the precast in the concrete modeling, concrete industry is not as not as advanced maybe in using a 3D model to model all the concrete or the interface between the building facade that might happen or the structural steel. So we do concrete and precast modeling on certain jobs. We may just do partial reinforcement at congested areas where you have a lot of embeds and steel anchor bolts coming in, or a lot of bars running both ways, or we may go ahead and detail all the reinforcing in the drawing as well. A lot of times this is required on several of our international products over in Moscow. Is actually that the engineer of record produced fabrication drawings for the rebar. This shot is just some of the precast modeling that we did on New Meadowlands Stadium. And the reason we did it there was to check clearances and drop stem clearances with the horizontal bracing that goes in the rakers and that. So we just modeled the precast as parametric components. We didn't put the pre-stressing in or the reinforcement in it. We just modeled the shape of it basically so that you could see once how far it was clearing the bracing. And it worked very well. We ended up having one clash on the whole job with the precast and the horizontal bracing. And the reason it was is because the precaster actually read the drawings wrong and made his stem 6 inches too deep. So if had he made it the height it was supposed to be, it would have cleared by about 2 inches. So here's just kind of a shot of how we use Tekla structures to look at congested areas. It helps a lot when we're working, visualizing it just for the contractors just here when they're placing the rebar and placing the embeds is a big help. I mean, you send them a couple snaps like this that they can access on their computer. They don't have to have Tekla structures to access this. So you just send them some snaps and they can see how the embed's supposed to go in, how the bars are supposed to go in, because as you know, it's not always that easy to get everything into those congested areas, and you know, they may say, oh, it can't be done, and if you show them it sort of can, but you have to put some thought into it, and really it gets pretty meticulous at times, and try to coordinate all that stuff in-house and show them how to do some of that. This is a baseball stadium in Tulsa, Oklahoma, where we actually modeled the foundation, all the concrete, and then went ahead and modeled the steel on top of it, produced the drawings. The lower right shows the drawing that was produced actually out of the shop drawings. Our design deliverable was a set of 2D drawings that came directly from the Tekla structures. We also provided the Tekla model available to the contractor if he wanted it. So our production model, how we actually go about and execute this work, is basically, or for the BIM model, is there's one model. There's a one model design process. There's one model that's carried all the way through detailing, one location for all the information, and there's only one model to maintain and coordinate. We don't want to have to run a parallel Revit model in order to get drawings out, or a parallel CAD model. We want to use the structural model, is also the detailing model, is also the drawing model, drawing production model. Less chance of having conflicts or errors between two different model sets. The one model design process, we usually use it. One model is used in-house as the geometry or the master model. The pieces in this model are used for analysis. So generally, we may actually start the model in something like SAP or in structural analysis program, bring that geometry over into Tekla, and then work with that to produce the drawings and everything. The analysis results are incorporated in the master model. We'll read out shears and reactions and everything else and put that into our master model as well. And then the trades are coordinated with exports of the master model to maybe Navisworks, or some people will coordinate within Tekla, or we'll take the Tekla model and do an IFC format and send it to the architect. One location for all the information. That's a great thing about Tekla, is that it's got you can store so much information in there. You can do the size, the location, the loads, the cambers, RFIs, anything. You have a complete tracking system from the start to the finish of how you actually got to someplace. The data is maintained and expanded throughout the process. So as you start going in, maybe right away you just put in the material grade. As you go on, then you realize you need CVNs on it. You go on, and there's an RFI that changed the paint color or the paint coating system on it. We can track all this stuff within the model. And that's the biggest thing, is, again, the one model is really the key to the thing. There's no more making sure that the models match. When we had first started this, we carried a parallel Revit model with a Tekla model, and it was a real pain to try to match those things back and forth. It seemed that we were using Revit because that's what the architect required or wanted. It's also what our technicians were familiar with, so it was easy for them to get drawings out and we didn't have to retrain them into Tekla. But carrying a parallel Tekla model with the Revit model was not a little short of a nightmare is all, because you never could be constantly exactly the same between the two models. And it reduces a lot of the hours and review and copy check time by having just a single model. You can just go through the one model. The engineer's familiar with it. They can get around in it. The techs are familiar. We actually have structural steel detailers on staff which can detail directly from it. So everybody's working within that single model. Now I've just got a couple of case studies here as we go through. There are different projects where the approach was a little different. Washington Nationals ballpark, it was a design build. It had utilized an IPD approach. And so using the tools or the different levels of tools we have from our construction support and advanced project delivery, we'll custom tailor an approach to a project based on what's going to produce the best value for the project. We may not detail all the way through on a job. We may not design connections on a job. We may only take it apart to a certain level. If it saves time or schedule or is a value to the owner, we'll take it to that level and then turn it over. In the Washington Nationals Park, we had basically about 3 months to start to mill order. It was required an architectural early sign-off, which is the biggest thing early on is making sure the architect's on board with you. You get a good concept, you sign off early, and so you can order the steel. On this project, what we ended up doing was a Tekla mill order model. That's as far as we took it, and we handed that over to the fabricator and the contractor, and they ordered the steel from that, took that model, and then went on through detailing. So we just did that early in the process to help get over the initial hump of getting all the modeling done and in the right spot. You know, the result is that the project opened from concept to handover. It only took 26 months. You know, the project team was excited and met all their obligations. The owner was able to open on time. So, you know, as a result, the team overall won, but unfortunately the Nationals are still losing. This is just a couple of model shots. You know, we did take a couple locations and detail in a couple of the connections just to give them an idea of, you know, what it was or what our intent is, and you can see kind of the actual field condition shot versus what was in the model, which we found has been very helpful for the field too. If you have a 3D model that they can pull up in the field and rotate around and look at, it helps the iron workers and the concrete guys understand what they're building out there. Another case study was Yankee Stadium. This was a little different approach. It was design, bid, build, but it was a design assist in that early on in the project they had brought a steel fabricator on. The structure is obviously iconic. Navis Works was what the CM was going to use in the end. We did model it in Tekla structures, as you can see, and provided that to the CM to help coordinate things with. Again, a very successful project. It worked out very well for everybody involved. It was a little different approach to just handing over 2D drawings, and you know, we were sitting in the room more consistently. We designed connections on this one. We built the 2D model. We built the 3D model for the members, and we partially connected it. We put in representative connections of the difficult ones and then handed it over to the fabricator. As a result, the team won, and of course, the first season that building was open, the Yankees won their 27th World Series. This is part of the iconic frieze, and this is where we use Tekla structures to coordinate a lot with the architect. This was a very important, iconic part of the old Yankee Stadium, was the iconic frieze that goes all the way around the top. We wanted to be able to replicate that or get pretty close to exactly the same thing in the new stadium. So we modeled it in Tekla, as you can see over on the right, and showed them how to, you know, how we were going to connect it with the bolts. You know, of course there were no bolts in the old one. It was either rivets or all welded together. But the architects were real particular, and as well as the owner, about, you know, how this was going to look. They wanted something that looked almost exactly like the old building. And so, you know, by modeling it 3D and being able to rotate it around and coordinate with this is how you know, Tekla structures helped us a lot in coordinating with the architect to get them what they wanted, and as you can see, exactly what we modeled is really what they ended up getting. So everybody was pleased in the end of how that turned out. This is a shot that was provided by the CM. Basically, he took our steel model and coordinated MEP with it. There's a lot of MEP piping and units and everything else that go in on this ground floor of all stadiums or arenas. Meadowlands Stadium, another case study. This one was a design build, design assist. Again, the fabricator was brought on early in the process, so he was allowed to provide some input. It was about 27,000 tons of steel. It was only 27 months from schematic to topping out. That's, you know, a little over 2 years, but that's from the day that we started on napkin sketches and ordered the columns until we topped out the steel was 27 months. And actually, using this approach, we ended up being, steel was obviously on the critical path from day one. We ended up getting far enough ahead that the steel was actually 3 to 6 months ahead of schedule, and they actually told the fabricator or the erector to kind of slow down because you're getting too far out in front of us. So that's not a bad thing necessarily to be is ahead of schedule once. What we did on this one was we modeled, we used Tekla to model the steel. We designed the connections with fabricator input, and then modeled representatives, a good majority of the steel connections in the model before turning it over to the fabricator, who then finished it with the shop drawings. As a result, you know, the Meadowlands Stadium opened on time. Everybody was pleased that we were able to make this tight schedule, and as a result, the team, it was a win for the team from contractor to owner to designer. Again, just a shot or two of, you know, how you can cut the model. You can show them how it's being built and that out in the field. The nice thing was originally we had not planned on modeling the precast. The CM wanted us to model, came back to us later and said, well, can you model the precast, because what we want to do is use it out in the field to RFID track all the pieces of precast. Not only that, we can see once what our progress is, whether it's in the shop, whether it's been in the shop, whether it's being shipped to the site, whether it's laying in the yard, or what's been erected. So when they pull it up to talk to the owner and even show them pay requests, they say, oh, well, here's where we were last month, and they, you know, oops, I'm sorry, and it gets all color coded, and then they say, well, here's how much progress we made this month, and it's all color coded. It's a very visual tool to help, you know, the CM justify his pay requests, as well as be able to track every piece of precast, knowing exactly where they're at in the field on it. The Kauffman Stadium scoreboard. This is actually the first job that we provided steel shop drawings on. It was never intended that we were going to do a Tekla model on this one to start with. We started regular Revit. Designers designed the drawings. It was a design bid build, so it was 2D drawings. They bid the project. Small local fabricator won the job. After they awarded it, they realized that this scoreboard the CM actually realized that there was a 3-month schedule bust. This scoreboard had to be in place by a certain date, and there was a 3-month schedule bust. So what we did is we took the actual Revit model, converted it into Tekla, cleaned up the geometry, and started doing the shop drawings. So they, well, did the advanced bill first, so they could order it, and then did the shop drawings for them. It helped cut down the review process time. It helped cut down the you know, getting somebody else on board, questions to the engineer. It was easier to handle in-house. We would just be able to ask the designers as my group was detailing this. You know, you do have to kind of throw away or put to the side. You have to put, when you run into a problem like this, you have a 3-month schedule bust, and the objective is to complete the job. You kind of have to put away all the walls. You have to knock down the walls of what's gonna, you know, what's gonna stand in the way of what. You know, we all have to work together to figure out how this is going to come together. It'd been very easy to throw up a wall and say, hey, look, you know, not our problem. We're the designer. We gave you the design when you needed it. You guys need to figure out how to get it done. Instead, you know, just by being a little open, wanting to work with them, be able to propose different ideas or methods of how to take something on. And it ended up being a good deal. They got it all done. We built a real good relationship with the fabricator and the contractor of being someone that'll step up and help them through their problems, not just you know, wall off. And as a result, the team won, and the project team won. I can't say the Royals are. And of course, they opened on time and on schedule. And that's just you know, a Tekla model with the shop drawings that were produced, some of the deliverables that were produced out of it. Now, this doesn't always, although most of my jobs that I've just showed you were all on sports, our Kansas City office concentrates mainly on sports. We also do other jobs, and it can be used. And I also want to show you it doesn't have to be the magnitude of a Meadowlands Stadium or a Yankee Stadium to make a process like this work out well. This is a Cathedral of Hope job. It's down in Dallas, Texas. It's only got 60 tons of steel. It was a design bid build project. Very complex geometry. I mean, the architect gave us a surface rhino model and said, here, make your steel fit in this building envelope. It was difficult in that our columns had to fit inside this wall cavity, but there's really no grid lines. I mean, you could have put 2 columns on a line and that was it. So we had to do everything with coordinates. We used their exterior wall, set all the coordinates and everything, modeled in where the steel needed to go, shared that back with them. We then designed the connections and modeled the connections in. We then turned that back over to the owner to actually bid the project to his fabricators and his contractors, because with this complex geometry, it's very difficult to take, if you can imagine, take plan elevations and sections and create this into a 2D. We needed to show it 3D. We needed to show what complexity was involved. Originally, before we had done it, they had two people looking at it. One guy did a material takeoff and came up with 50 tons. The other one did a material takeoff and came up with 120 tons. And truly, from the model, in the end, it was 60 tons. I mean, it's the difference between night and day when you're trying to bid a job. And as a result, I think the owner was able to gain, you know, he had a model, we shared it with the fabricator, they were able to get a good price on the job, a fair price on the job that was still a, you know, and define the complexity for him. If you take the complexity out of a job for a contractor, or at least help him understand the complexity better, you're going to get a better number. You know, and this is just an example of, you know, the connections that we had in there, how we made the 3D isometrics, how we showed them how you were connecting things in the model, which helped, you know, helped cut down on his uncertainties of how things were going to go together. Case study, Morgan State University. This is a little different. This is a design bid build job. We did no structural steel detailing on this. We did concrete detailing and building facade modeling. The contract was written such that the CM wanted a Tekla model or Tekla usable model from all of his subs. And so the subs were responsible for modeling and providing a coordination model back to the CM. Actually a Barton Mallet job. And so the concrete guy, you know, good contractor, just was not that familiar with providing 3D BIM models. So they started and hired somebody in Revit to do some rebar and reinforcing and detailing this. It really didn't come over or translate very well. These guys may know more about the job than I do on that part of it. But the concrete guy called me and said, hey, I know you do Tekla. Can you do Tekla for us? And can you get it to come over in IFC format so we have all the rebar or the DB1 files from Tekla so we can coordinate this stuff? So we took on that originally and produced the concrete. He already had the rebar drawings that he had done 2D hands, so we actually took the rebar drawings. We modeled all the concrete, the parametrics. We put in the rebar from his rebar drawings and found 29 or 30 conflicts where the drawings were different than what his detailer had actually detailed. So we sent back this list to him and said, hey, we need to resolve all these items, which I think was a big help to the contractor because he would have went out to the field and found he had 30 field issues eventually. He would have had the rebar fabricated to this, he would have sent it out, and he would have had all these field issues, which, okay, they probably could have, you know, cut and torched and tied in some more bars, but still it was something he didn't have to deal with by going through this. Building facade was kind of the same way, as we modeled the building facade for help of coordination with the overall structure and the routing and everything else. So we did the building facade model and the concrete detailing, and it's nearing completion now in construction. I'm kind of working on finishes now, I believe. The last one I've got is a design build project, and that's where this process really, in my mind, is what it's really intended to and where it really works well. This is the Quantico aircraft hangar. You go in with a project team, you develop a concept from the start that everybody is on board with. The engineer then takes, you know, goes through and designs the process, designs the building along with the fabricator being on the team and the architect. You can share models back and forth constantly. The engineer then keeps on going and designs the connections with fabricator input, can model the connections, and can produce the actual shop drawings in the end. You're now getting it to, you're cutting down the number of team players on a number of entities that are in your team. You're making it more a sole source representative here, and you can utilize all these different approaches in modeling not only the foundations but also the concrete, and it comes together in a very well coordinated project. So with that, I guess that's the end of my part of my presentation. So hopefully I've given you an idea of how we use Tekla from the start, from concept all the way through design for coordination with the architect and into construction and turnover. Thank you.